Sean todos ustedes muy bienvenidos al Seminario Departamental del CICATA Querétaro, que en este semestre es coordinado por Luis Miguel. Luis Miguel, muchas gracias por recibirnos. Stan, please be very welcome. I give you the warmest welcome to the National Polytechnic Institute. It's truly an honor to have you here, and let's go ahead. So let me talk to you a little bit about our speaker today. Stan Birchfield is a principal research scientist and senior research manager. He explores the intersection of computer vision and robotics. Prior to joining NVIDIA, where he works currently, he was a tenured professor at Clemson University, where he led research in computer vision, visual tracking, mobile robotics, robotic manipulation, and the perception of highly deformable objects. He remains an adjunct faculty member at Clemson University, and he also conducted research at Microsoft. He was the principal architect of a commercial product at a startup company in the Bay Area, co-founded a startup with collaborators at Clemson, and consulted for various companies. He has authored or co-authored more than 100 publications and a textbook on image processing and analysis. And his open source software has been used by researchers around the world. He regularly serves on the program committees and editorial boards of various leading conferences and journals in computer vision and robotics. He received his PhD in electrical engineering with a minor in computer science from Stanford University. So again, Stan, thank you very much for making the time to be with us today. And please go ahead and proceed with your talk.
Okay, excellent. Thanks again, Joaquin, for inviting me. It's good to see you again. Thank you all for coming. I hope this will be worthwhile for you. To be clear, is this a 1 hour? Do I have 1 hour or what?
We have a 1 hour total, but that usually we make time for questions and answers.
Okay, so 1 hour including questions and answers?
That's correct.
Okay, sounds good. I should mention that I'm still figuring out the Zoom thing, so I don't know that I'll be able to see participants while I'm presenting. So if someone has a question, you just unmute yourself and speak. We'll keep this informal if you'd like. I'm afraid if you try to raise your hand or do something fancy, I may not see it. So, all right, let me figure out how to share my screen. Are we good there? Trying to get this to not block your view. Okay, well, let's try this. Is this good?
It is perfect.
Okay, good. Okay, so so thanks again. My name's Stan Birchfield. I work at NVIDIA now. I'm a manager there and also a research scientist. And the title of my talk is Sim to Real Transfer and Robotic Learning. So my background's all computer vision, but I am primarily interested in applying vision to robotics applications. I've done a lot of mobile robots in the past, but I'm now focused more on manipulation. Here's just kind of a sampling of the robotics work that's being done at NVIDIA. So at NVIDIA, we're heavily investing in robotics. Our mission is to tackle the hardest problems, and robotics is certainly one of those. And we want our GPUs to be the brains behind intelligent machines around. And as such, we have multiple teams around the company looking at problems such as perception, planning, control, and so forth for navigation, locomotion, and manipulation. So these are some pictures of our robotics lab in Seattle, led by Dieter Fox, who's a professor at University of Washington, and then I and some colleagues of mine work in a different building outside in Redmond, which is about 30 minutes away. So it could be argued that we're on the verge of a revolution in robotics. Robots have the potential to fundamentally change the way we do a variety of activities, helping elderly and disabled people live more independently, assisting doctors and nurses in healthcare, environments to take care of patients, to work alongside people in manufacturing, to enhance productivity. And this revolution is going to require solutions to many longstanding research problems. So our mission at NVIDIA is to drive this transformation. Existing robots generally fall into one of two categories. First, there are the robots whose sole purpose is navigation, that is getting from point A to point B. And these are being increasingly used in logistics and delivery settings. And for these robots, the problem is two-dimensional. The primary goal is simply not to collide with anything. At the other end of the spectrum, we have manufacturing robots whose goal is to follow a specific trajectory in three-dimensional space and to do so repeatedly. And these kind of robots are not aware of their surroundings. They generally don't have any sensors, which makes them dangerous. And therefore, they have to be put generally in cages, because if someone were to interact with them, they could get hurt. And so the question is, how do we get from where we are today, which is robots that for the most part are blind and dumb and dangerous, to where we want to be, which is robots that are aware, smart, safe, lightweight, agile, and helpful. So researchers around the world are tackling a variety of problems in robotics, from hardware to perception to planning and control. And no doubt these efforts are needed, and we're working on many of these ourselves. I will show you a few of them here. Perception, tactile sensing, planning algorithms, natural user interfaces, better hardware, hands, and so forth. And I think it's only through this multidisciplinary collective effort that we're going to make progress. But today, I'd like for us to try a thought experiment, which is, so I don't know how many of you are interested in robotics versus vision and so forth, but suppose, for those of you who are interested in robotics, if you could focus on only one area, what would that be? Which area do you think is the single area that's most likely to make the sort of revolution possible, right? To enable significant breakthroughs in robotics?
Reasoning?
Yeah, anybody want to answer that? Sure, you have thoughts?
I think
reasoning, okay. Reasoning, yeah. Yeah, I think a case could be made for any of these, right? I think that progress is needed on all of them. Reasoning could be arguably like right up there at the top of the list. I think sensing could be argued to be near the top. Hardware, I mean, I think any of them could be. So it's a good, yeah, it's a good idea. To dig a little deeper, what I want to do is think about the deep learning revolution, right? So if we kind of take a step back and remind ourselves where we are with regard to this, if we look at computer vision, speech processing, natural language processing, and these other fields, these fields have been just absolutely turned upside down, revolutionized. Things that we didn't think were possible 10 years ago are now possible. Problems that we thought would take 50 years to solve or so are already solved in these fields. And the reason is because of deep learning. So what has enabled deep learning? Well, it's primarily three things, as many of you probably already know. There's fast compute, there's big data, and there's advanced algorithms. And if we look at these three things one by one and apply them to robotics, I think we'll gain some insight as to maybe why robotics is so much lacking. So first of all, we have fast compute, right? So the compute really, though, is already there, right? So the same compute that's available to the other fields is also available to roboticists. So this is already happening. And as you know, NVIDIA has been kind of at the center of this. Our GPUs have been absolutely essential here, right? And then the algorithms, I would argue, are variations on a theme, okay? So that's not to say that work won't continue on algorithms. We need network architectures. We need more algorithmic advances and so forth. So I don't want to minimize any of that effort. But I think to a large extent, the convolutional neural networks, the CNNs, the recurrent neural networks, the RNNs, and then if you go to deep reinforcement learning, the major algorithms are there in place, right? So that work will no doubt continue, and it's important. But I'm trying to make the case that that it seems likely that those are going to be sort of incremental advances and variations on a theme, as opposed to some kind of fundamental breakthrough. Whether you are convinced by that or not, it's up to you. But the third area I think is really interesting, which is big data, right? So the question is, where are we with big data? So without big data, computer vision would not be where it is today, right? So large labeled data sets were needed to train the algorithms that we have today. And that even larger data sets are needed to go beyond those problems to newer problems and to bigger and harder problems. And so that leads us to the question of, well, where is robotics today with regard to data sets, labeled data sets? So computer vision, as you know, there's a large number of sizable data sets that have been collected over the past decade or so. And these have been used to train deep neural networks for scene recognition, for object detection, segmentation, and so forth. And then if you notice with the harder and harder problems and higher dimensional problems, there's sort of this transition, natural transition from, well, it's natural, but it's a transition from real world images to synthetic images. So for example, in optical flow, networks are generally trained exclusively on synthetic data because it's too time consuming, too difficult, impossible to label real world images with the ground truth optical flow. And so you have these things like Flying Things 3D and Centel and so forth. In robotics, in contrast, I mean, there are data sets, but they're a much smaller number of data sets and they're smaller in size generally. Moreover, many of these data sets in robotics involve perception only. And they don't really go beyond what you would expect in a computer vision data set, whether they're like for self-driving cars or mobile robot navigation or watching activities like cooking. And then there's some other data sets that do focus more on robotics problems, but they tend to be low level information like haptic data or force data from pushing and so forth. And so we're starting to see a few multimodal data sets for challenging manipulation tasks, but we still have a long way to go. And of course, in robotics, a static data set's not enough. Robotics inherently involves closed loop processing in which actions taken by the robot affect the environment, which in turn affects the data which is available to the sensors. And so what's needed is an actionable environment in which an algorithm can be run on an embodied agent. So this is useful not only for collecting data for training, but also for quantifying the performance of algorithms and for comparing algorithms across labs. And so thankfully, we're starting to see an increasing set of such simulated actionable environments. But for the most part, these are fairly simple scenes with a single actor in a small environment, limited interaction with the environment, and not really too much photorealism in the appearance of things. Okay, so to rephrase our question from before about what will be the key, or one of the main keys to unlock the robotics revolution, similar to the computer vision revolution. So the question is, well, is it possible that simulation is going to be that key, right? Or one of the main keys that will do this? So I think if we want to analyze this question, there's really only three possibilities. So first is the view that simulation will never be good enough to succeed. So this was championed by Rod Brooks decades ago in his well-known quip that simulation is doomed to succeed. And what he meant was that simulation can be used to predict anything we want. And so there's no guarantee that the predictions from simulation really have anything to do with performance in the real world. And I think this was a valid point of view 20, 30 years ago when he made it. I think there's still some truth to it today. I think we have to be careful. I'm a big fan of testing algorithms in the real world to ground our science and convince ourselves that it actually is working. Because if we just live in simulated world, we'll sort of never know. Well, it's easy to convince ourselves that things work that may not actually work in the real world. On the other hand, I think a lot has changed in that 30 years since he made this statement. So the opposite extreme is that without simulation, these interesting robotics problems will never be solved. We can't hope to make any progress without them, right? And that's maybe a point of view that some people would espouse. I'm going to advocate something in the middle. And what I'm going to advocate is that while progress can no doubt be made without simulation, that's fine. But I think eventually it will mature to the point, and we can debate when that'll happen, but I think it'll mature to the point where simulation will be useful for solving real robotics problems. That is to generate training data, validate solutions, and so forth. And we're going to find that, I think we're going to find that some problems are so complex that as we try to tackle them, simulation actually is critical. So robotics will not only benefit from it, but some problems may actually require it. And this is because simulation is really, I think, the only way that I can think of to generate massive amounts of data with high consistency in an economical way for robotics. So maybe I should stop here and see, are there any feedback, any thoughts, questions?
The thing is that apparently we have muted like everyone because some time ago we were hacked and but
okay, that's fair.
We have a question. Well, it is in the chat box. Would you like me to read it, or?
Yeah, if you could read it, that would be great.
What will be the relevance of quantum computers in robotics in the coming years?
Okay, well, the relevance of quantum computers. So I'm not a quantum computer expert by any means. What little I know about quantum computing is that it's it's a revolutionary idea that allows us small set of problems to be solved very fast. It's not, as far as I can tell, it's not really designed to be a general purpose computer. And so I don't know, I think it's anybody's guess how that will affect robotics. But
we have another question. How much cost to generate massive data, for example, for computer vision, like 3D cars?
what was the first part of the question?
How much does it cost to generate massive data?
Oh, how much does it cost? Yeah, so the cost is really in the labeling. So collecting the data is not so bad. The problem is after you collect the data, you have to label it and you have to pay humans to label it. And so that gets very, very expensive. Possibly, I don't have a number for you, but yeah.
Possibly what Alejandro means is what does it cost in terms of the synthetic generation of data?
How much does it, sorry, how much does it cost to generate synthetic data?
Yeah, to simulate a scenario and from it generate synthetic data.
Okay, well, what we like to say in our world is that simulated data is free, right? It's obviously not free because you have to have a computer and you have to have maybe a GPU or something, and you have to have, you know, time to generate, but essential, and you have to have the environment modeled. So at the current state of affairs, you have to have some kind of artistic tax paid to model the scene and so forth, right? So right now there is a non-negligible cost to kind of get these things up and running, but the nice thing about synthetic data is once you have it up and running, once you have a scene and once you have actors and once you have a framework that allows you to put those actors in the scene and maybe randomize them, and the tool, if the tool is set up to already generate the ground truth for you automatically, which it should be able to, and many existing tools can already do that, then it's just a matter of, you know, pressing a button and waiting some number of hours, right? It could be 2 hours, it could be 12 hours, something like that, but it's not generally a long period of time. And then in that case, it does come for free, right? You get your data, you get your labels, and then you can use those to train your data set. So in the problems that we've solved that I'm going to be talking about later in the talk, I mean, that's generally what we do is we have a tool. Sometimes they're tools that we developed in-house and have made open source. And then sometimes they're tools that we find out in the community. We use these to generate the data, and then we can train the network using that synthetic data. And then once we've trained it, we can apply it to real world scenarios. And in that case, we like to say that the data comes for free, which is you know, a slight hand waving, but it's not completely far from the truth.
So these are the questions that we have now.
Okay, great, thank you. If you have more, feel free to interrupt me.
All right.
Okay, thanks. Okay, so let's continue. So we're still talking about simulation, and I want to make an analogy here. So if we think about airplanes like robots are complex closed loop systems where safety and performance are critical. And whereas early attempts to flying largely relied on trial and error, modern systems rely more and more on simulation to achieve good performance. And so eventually, if you look historically, what happened is we reached the point where the complexity of the machine and the maturity of the simulation dovetailed. So you kind of need both of those, which enabled designers and operators to achieve performance that would not have been possible otherwise. And so today, modern airplanes are designed entirely in simulation, or some of them are designed entirely in simulation. And the simulation is used throughout the industry, not only designing the aircraft, but also for training the pilots, which enables them to encounter rare situations that are much more difficult to capture in the real world experience, and for testing the aircraft and so forth. So in the same way, I see simulation as the future of robotics. And another argument, just to kind of further this, is that if large data, if you accept the fact that large data is needed for progress, okay, which is what we've seen in computer vision, then the only alternative to simulation, I think, is real farms of real robots, such as the ones you see here. But of course, a farm of robots like this requires an extraordinary investment of infrastructure and maintenance. And so only a few organizations with very deep pockets can afford to do this sort of thing. So if we want to progress to a world in which you know, robotics learning and robotics algorithmic development and so forth is democratized, where not just one or two companies in the world can do this, but sort of, you know, any reasonably sized lab or researcher group can contribute, then I think simulation is a much more plausible path than, you know, real robots like this. So okay, so all that was basically just to kind of motivate why we should do sim to real in robotics. So simulation to reality. Hopefully you found that somewhat convincing. If you didn't find it super convincing, maybe at least you're convinced that it's a plausible way forward. Okay, even if it's not the best way forward. So we're going to go with that premise for the rest of the talk. Okay, so let's make sure we're in agreement on what's involved in sim to real transfer. So we have an environment that provides simulated observations, and we have an agent that takes actions in the simulated world to change the state of the environment. And we change the state of the environment that then affects the next observation. Okay, and so what we want then is a policy pi. So we have this, yeah, so we want that as a policy pi down there at the bottom that maps the observation to the next action we should take. And so what happens is in the simulation, we train a neural network to represent the policy. And our hope is then if the simulator generates photorealistic observations in the form of camera images, and if it so there's photorealistic on the left. And at the same time, if it's modeling actions in a physically realistic way, then we take the policy to a real environment, we can expect it to work. Okay. So if any of you are old enough to remember flight simulators from say 30 or plus years ago, they were extremely crude. And what's interesting is if you put them side by side with a robot simulator of just a few years ago, not too long ago, you'll see kind of a similarity there. And so I think decades from now, we're going to look back at these robot simulators like I have shown here, and we're going to view them the same way that we look at these early flight simulators, right, from the 80s. So compared with what we'll have then, we're going to see these as fairly crude because they don't model physical reality very well, especially contact forces, and they also don't produce realistic imagery. So on the other hand, just as flight simulators have progressed since 1983, I think it is to be expected that robotic simulators are going to progress over the coming years and decades. And we're already seeing hints of this. So in the gaming community, they've been working very hard to solve problems that are very, very similar to robotics. And so here are a couple of recent developments in NVIDIA showing that some of the major components are already in place or very close to being in place. So on the left, you have this RTX ray tracing GPU, which is a major step forward in computer graphics because it's able to generate photorealistic images in real time. So the images that you see from a movie, for example, are oftentimes they're photorealistic, but they have to be rendered in massive rendering farms over a long period of time. It's very expensive. It's kind of a one-time deal. Whereas here, the door has been opened just in the last year or so for real-time ray tracing, right? Which can then be incorporated into a computer game. So I think this is a revolution that's happening in the computer gaming industry, which also can and will affect robotics, right? Generating training data for robotics and so forth. And on the right-hand side, we have a physics engine developed at NVIDIA that is been going through a number of iterations, and the more recent iteration here, one of the more recent iterations here shows that it's able to do a better job of modeling articulation and context. And so what's needed now, I think, is to take some of these technologies from the gaming industry and so forth, bring them together and go beyond gaming to do real robotic learning. So whenever we talk about simulation, we have to talk about the reality gap. The reality gap is the discrepancy between simulated data and real data. And because of the reality gap, a policy trained in simulation may or may not work in reality. So there are three ways to deal with the reality gap. So the first way is to increase the fidelity of the simulator. So this involves both the physical modeling as well as the photorealism of the generated images. And progress on both of these fronts is rapidly being made, which is what we showed in the previous slide. Nevertheless, the simulation is never going to be perfect. So although the reality gap can be reduced, it can never be eliminated completely. One way to bridge the remaining gap is to intentionally learn a mapping between the two domains. So this is known as domain adaptation. And we've made a lot of progress on this as a community, but I'm not going to talk about this due to time constraints. I'm just mentioning it, and then we'll move on. The third approach, however, is something that we have used significantly in our lab, and I'll talk about this, and that is to make the controller robust to imperfections. So this can be done using domain randomization, which is what we use a lot. It can also be done by adding noise during training, or using or adding or making the policy stochastic, so it can deal with uncertainty in the input.
One question.
Yes.
In your experience, how well do simulator trained models using reinforcement learning techniques perform once they are tested in real environments?
So how well do simulated policies trained using deep RL?
Simulator trained?
Right.
Do they transfer to the models?
Yeah. Yeah, so I think it's. I mean, this is why research is fun, right? Because these questions we don't know the answer to, right? I have an opinion. So when I look at most papers that try to do end-to-end learning with reinforcement learning, or like end-to-end reinforcement learning, like from pixels in to like torques out or joint motor commands out, I think they oftentimes result in robotic motion that would not be acceptable to like an old-fashioned like true roboticist, right, who's used to smooth trajectories and so forth. You end up with these kind of motions that aren't super realistic. Toward the end of the talk, I'll show you some recent work that we've done where we use deep RL to train a network and then apply it to the real robot, and we actually get smooth policies. And in that case, we don't have perception plugged in yet, so that could be part of our success, but I don't think that's really fundamental to it. I think what's more likely is that it's because of the way we're formulating the problem and the way we're training it. And so I'll talk about that when we get there. That's a great question.
And another question.
Yep.
How can the use of adversarial generative networks techniques contribute to this by generating photorealistic images? Yeah,
so GANs, or generative adversarial networks, are an exciting technology that's come out in the last few years, and has the potential to bridge this gap by generating photorealistic imagery. Yeah, for sure. We haven't ourselves looked at it. There are other people in our group at NVIDIA who have spent a lot of time looking at GANs. I think there's a lot more that could be explored in that area, for sure.
All right. Thank you.
Yep. Yeah, great questions. There has been a fair amount of success in this idea of sim-to-real transfer in robotics. This is from various research groups around the world. And what they've done is they've shown, this kind of answers your question, right? They've shown that it's possible to train policies and simulation that then apply to the real world. And that's true for things like locomotion and manipulation of rigid objects on a table, towel folding and so forth, bin picking, and stable quad rotor flight. So I think these are just a handful of the success stories that I've seen in the literature of sim-to-real transfer in robotics. And each of these techniques has different assumptions, different modalities in terms of sensing, and different goals in terms of what the robot is trying to accomplish. So we have a long way to go, but I do think these are promising results to encourage us to continue working on this. So that kind of transitions me now to highlighting some of the work that we've been doing here at NVIDIA in our group and some other groups that we collaborate with. So what I want to do is talk like for the rest of the talk on some of this work that we've been doing. And I've broken it up into two parts. So navigation and manipulation are at the top and bottom. And then from left to right, I'm going to talk about some techniques that are just perception only. And then on the right, some techniques that are actually involve closed loop control. Okay. And then within these four categories, I'm going to talk about 5 different projects. So first, let's talk about detecting vehicles and images. So in this work here that I'm showing you, what we're using is domain randomization. So domain randomization is where you randomly apply textures, poses, and distractors and so forth to the image to generate a training data set that has enough variation in it that hopefully, so the hope is that once the network is trained on this variety of images, then when the network sees a real image, the real image just looks like another part of that variety. And so in this case, we're sacrificing photorealism for variety. And so we randomize all these components, then we put everything in front of a background image, which is also random. We train the network to detect cars, and then we apply it to the real world. That's domain randomization, and other people have done that. What we propose in this paper is something called structured domain randomization. So the idea here is that if you use the technique of a domain randomization to say learn to find cars, it'll work fine as long as cars are big enough. But when the cars get really small, then there's not enough information there. And so what's really needed is the context around the car to be able to make the decision. So if we look at the graph here on the left, this is our solution. What we do is we randomize the scenario, and the scenario on the left here, this S, is whether it's urban, suburban, or rural. And then from that, we randomize the global parameters, such as the number of lanes, whether there's a median or sidewalk, or so forth. And then from that, we then randomize the shape of the road, which is represented as a context spline. And then we randomly place objects on the road. And those objects can be, or in the scene really, when those objects can be the cars, pedestrians, trees, houses, and so forth. And so here's just some examples of some of the images that we created using this technique. So it has the advantage of domain randomization because it has lots of variety, but it also has some structure to it, which makes it more useful for training a detector, especially for these smaller vehicles as they recede into the background, whose evidence is largely due to the context around them as opposed to the actual pixels on the vehicle. And so this variety allows us to achieve, or at the time it did, allowed us to achieve state-of-the-art results on Kitty, the well-known Kitty data set. And that Kitty data set is divided into easy, moderate, and hard cases, which you see here on this plot. And that's largely due to how close the vehicle is to the camera as well as occlusion. And so the bars show the accuracy of the exact same network trained on different data sets. So larger values are better, and our approach is in green. And you can see that our approach successfully bridges the reality gap. So what's interesting is we beat not only domain randomization, which is kind of the baseline, but we also beat some photorealistic synthetic data sets, such as SEM 200K, which, if you can tell from that number, 200K is a lot of images. So we're only using 25,000 images. They have 200,000 images, and we get better results. And then what's also interesting is we're beating virtual Kitty. This VKitty here is a data set that was handcrafted to mimic the actual Kitty data set as much as possible. So the placement of the cars, the angle of the camera with respect to the road, all of these things were carefully tuned as much as possible to make that data set match the testing data set. So in all these cases, we're training on synthetic data, but then testing on the real data. And so even though virtual Kitty has kind of this unfair advantage over us because they're training on images that are carefully tuned to be like the test set, just the sheer variety of images that we're generating from this SDR technique allows us to get better results in these cases. And then the other interesting thing about these results here is that we're not only bridging the reality gap between synthetic and real, but there's also a domain gap between different real data sets. And so a network trained on one real data set doesn't necessarily work on a different real data set because they're collected in different locations with different hardware and different assumptions and so forth. So what I think is kind of cool here is that the synthetic data has the potential to overcome this domain gap. And so, for example, this BDD 100K is a real data set. And if you train a network on the BDD 100K, if you train it on the training part of that data set and then test it on the same data set, you're going to get really good results because the distributions match. But in this case, we're training on the BDD 100K real images and then testing on Kitty. And you can see that our fairly simple method of generating synthetic data gives us better results than we would get if we trained on those real images, right? So the difference between the BDD data set distribution and the kitty distribution is sufficient enough that it doesn't really transfer from one to the other. Okay, and then here are just some results. So even though the network has never seen a real image, we're able to detect successfully all the vehicles in the driving lanes, as well as many of them that are parked on the side of the road. And so this video shows not only our ability to bridge the reality gap, but also the domain gap between two different data sets, because we're showing this on two different, on the kitty and on the cityscapes data sets. There's no temporal processing here. This is all just single frame detection. And yet the results are fairly stable continuously. Okay, so that was one project. And then I just want to briefly touch on the ability to do closed loop virtual worlds in driving. So at NVIDIA, we have two initiatives that we've announced. So in one case, on the left-hand side, this Drive Sim is a tool that enables the user to create a virtual world. So it's kind of similar to that SDR that we just mentioned, except this has a human in the loop. So it's similar to our approach. So the road geometry can be selected, and then the scene can be populated with buildings and trees and fences and so forth, and the vehicles can be added to that. And then once you have a virtual world like that, you can import it into this Drive constellation, which runs the simulation and produces photorealistic imagery of the vehicle as it drives in this environment. And so you can imagine, again, for things like accidents or rare events that we don't want to actually have to, we don't want to have a real event of an accident, and in order to capture that data, we can use a simulator like this to do that in a safe manner, and in a way that allows us to disproportionately include those kind of events in the training, whereas in the real world, they may happen so rarely that they wouldn't actually affect the training sufficiently enough. And this kind of simulator also allows us to verify algorithms, right, before we deploy them in the real world. So these are two initiatives that the company is involved in. Okay, so moving from navigation to manipulation, I want to talk about the first project that I worked on when I joined NVIDIA a few years ago. So what we did in this project was we have a human that is demonstrating, this is a learning by demonstration. So the human is doing a demonstration of stacking blocks or stacking little toy cars on those blocks. And the camera is watching the scene. And then we want the robot to mimic that action by reproducing that behavior. And we want these plans that are executed to be human readable. So in this case, you have something like place the car on the yellow block. So we have three different neural networks. In this case, we have a network for perception, a network for inferring the relationship between these objects, and a network for generating the program, the human readable program. And in all cases, these neural networks are trained entirely on simulated data. And so, so we put this together, we read the paper, we put together the video and everything. But then there was this nagging question, which was, would the perception network that we have here that detects these blocks in the car and so forth, would they work on more realistic imagery as opposed to just these single colored cubes? And so then we went to the YCB data set, which if you're in robotics, you're familiar with this. It's kind of like the most widely known data set of objects in robotics. And there's 80 something objects in here. And of those 80 something, other researchers have whittled it down to a subset of about 21, which you see here. And then of those 21, we asked ourselves, well, which ones could we actually imagine grasping with our robot? So we have a Baxter robot that has a 4-centimeter travel distance. So the object can't be too big or it's not going to fit. It can't be too heavy or it's not going to fit and so forth. So we came up with this subset of 5 objects. The other constraint that we had is we needed to be able to go to the store and buy these objects. And surprisingly, the manufacturers change the logos very frequently and make it difficult to actually find an actual object at the store, even if you live in the same, I mean, we're not that far from Berkeley where they captured all this data, and I can't go to the store and actually buy a Jell-O box that looks like that Jell-O box. They don't exist. And we've looked everywhere. And so we had these constraints, and that led us down to these 5 objects here. And so then what we did is trained a network to detect those 5 objects. But before I go there, I first just want to put in a little plug for Some of our more recent work is we went and found a set of toy grocery objects. And these objects can be can be purchased from Amazon, just downloaded from Amazon for less than $50. And the idea here is that if we can train neural networks to detect the poses of these objects, then researchers hopefully around the world could then purchase these real objects and put them in their lab and use either our pose estimator or their own, and then actually do real robotic experiments with them. Okay, because I think the YCB objects just have this fundamental limitation that acquiring the physical objects is difficult. The other thing about the YCB objects is they have real food in them. And so with real food, it just makes it that much harder to purchase, you know, in other localities, right? As opposed to these are just cardboard, mostly cardboard or plastic boxes. And so they ship much better, much more easily without any kind of restrictions or anything. So what we have here is a set of 28 objects. They're toy grocery objects. The real ones are at the top. The synthetic renderings of the 3D models that we scanned are at the bottom. And then one of the images from our data set here is on the right. So we'll be, we're in the process of releasing this. So if you're interested, you know, contact me or just keep looking on the web and we'll have it up pretty soon. And this is, again, to kind of help the community go beyond the limitations of the YCB. Okay, but now having said that, let's go back to YCB. We have these YCB objects. We trained a pose estimator, and we call this DOPE, right? So DOPE stands for Deep Object Pose Estimation. And the goal of this work was to, from a single RGB image, detect every instance of the object, and then to recover its full 6 degree of freedom pose. And we wanted this to be robust to pose, to lighting conditions, to camera intrinsics, and so forth. So if we trained it in our lab, we could give it to you, and you and your lab could just run the code after typing in your camera intrinsics, and it would just work. So we have this code available. It's publicly available if any of you want to try it. And it's a very simple network architecture. It's based on a convolutional pose machine. So the image comes in. This slide is a little misleading because it looks like the object is cropped, but that's not actually true in reality. In reality, we just feed it the whole image, and it finds the object wherever it is in that image, runs it through a backbone, a VGG backbone, and then it runs through some convolutional layers. And then what comes out is a set of belief maps, and the belief maps have peaks at each of the 8 vertices of the cuboid, the bounding cuboid of that object. And there's also a 9th belief map for the centroid. And then we have a little bit of post-processing to group those together, to cluster them so we can find the individual objects. And there's a little bit more detailed here, but that's most of it. And then I don't know if my image, is that being blocked? Let's see.
We see the image just fine.
Oh, you can see it just fine?
Yeah, we see it fine.
Okay. Yeah, I can't tell whether what Zoom is showing me versus showing you. So, okay, cool. So then you see that we get this 3D bounding cuboid pose in full 3-dimensional space. And then because we have the camera intrinsic, the network detects everything in 2D on the image plane. And then we use the standard perspective endpoint algorithm, if you're familiar with that. It's just a standard algorithm from classical computer vision to then lift those points from 2D to 3D, given the dimensions of the object itself and the camera intrinsics. And so now we have the object in 3D. We have what's called a 6 degree of freedom pose estimation of that object. Okay, and then to train this network, we trained it only on synthetic data. We developed this plugin for Unreal Engine 4, which is called NDDS Dataset Synthesizer, and it generates near photorealistic imagery. And then we gave it the capabilities of domain randomization. And it exports not only the image, but also the metadata of the 2D bounding box and so forth, right? And the key point locations and so forth that we used for training the neural network. We do have a more recent, again, here's another plug, which is we have a more recent tool that we've released called NVISI. And this tool is able to generate more photorealistic images using ray tracing. And you can see here in the top image, we do things like motion blur and defocus blur and so forth. So it's sort of the successor to NDDS. and it also will generate metadata. And on the bottom, you see metadata, like from left to right, you see a clean image without the motion blur. You see the depth image. You see, I forget what each one of these is, but I think it's surface normals and instance segmentation and that sort of thing, right? So then we can use these things to train networks however we want to. And so, this tool is freely available if any of you are interested in generating your own synthetic data. But for this project, we used the NDDS tool, which is a little bit older, not quite as photorealistic. But what we did is we generated two different data sets. So on the left, we generated a domain randomized data set. So we took these YCB objects, we placed them at random poses in front of the camera with random lighting conditions and so forth, in front of a 2D image in the background, random 2D images in the background. And we trained the network using those, and we got some like reasonable results, but not state of the art. And then we generated a different data set on the right-hand side, which is more photorealistic. This is actually a 3D scene, and we took these objects and we let them fall under the weight of gravity, and they bounce around and they hit the table and they collide with each other. And then we trained a network using these images, and again, we got reasonable results, but they weren't state of the art. And then what we did is we learned if we mix these two data sets together and we train the network on both, then they complement each other to the point that we're able to get state-of-the-art results. So this is just a curve of one of those objects. This is the sugar box object. The blue curve is our algorithm trained on this dope algorithm trained on the domain randomized and the photorealistic data. And you can see that it outperforms domain randomized or photorealistic individually. And it also outperforms another state-of-the-art network called post-CNN. And then I have a little dotted line here, which is set at 2 centimeters, which is roughly the accuracy needed by our Baxter's gripper to be able to grab something reliably. And these are results on the 5 objects, the 5 YCB objects that I mentioned earlier, that not only that cracker box, but the other ones. And you can see that our photorealistic plus domain randomized data, when we use those to train the dope network, we get state-of-the-art results on 4 of those objects. The 5th object, we struggle a little bit. That spam meat can has a metallic top, and the NDDS dataset synthesizer that we're using at the time did not model reflection. And so we weren't able to generate images that looked sufficiently like the real images. But nevertheless, we found that dope trained on synthetic data outperformed one of the leading networks that was trained on synthetic and real data together. Let me just see how we're doing on time. Okay, I might need to speed up a little bit. These are the results of our dope network and side by side with post-CNN on some real images with some challenging lighting conditions, and you can see that it's more stable. Again, we're not doing any kind of temporal processing, so we could, if we filter these, we could get even better results. But even without filtering, they're fairly stable. Okay, and then now that we have this pose estimator, we can then use this to estimate the pose of an object, and then we can use kinematics and off-the-shelf motion planning to blindly grab the object in an open-loop fashion. So that's the traditional approach. And if all goes well, then the robot's able to grasp the object. So we've observed fairly consistent, successful graphs and of this variety of objects from different grasping directions in our lab. And so we have a chest-mounted camera that finds the objects, and then with proper calibration and so forth, and the robot's able to find the objects and grab them for pick-and-place tasks or hand off to another person. Okay, but any kind of error in the algorithm is going to lead to a failed grasp. So if the camera extrinsics are not properly calibrated, or if the camera gets bumped out of position, then there's going to be a mismatch. Or if the dope algorithm doesn't find the object just right, then it's not going to be able to grab the object. And so we asked ourselves whether there wasn't something we could do to make this better. And so what we came up with is a solution for closed loop grasping. So in this case, we use images from the camera to constantly feed back into the network to correct the errors in calibration or estimation. So we still use dope for the pre-grasp, and then after that, the closed loop processing allows the network to continually adjust itself. So this is our neural network architecture. We take an image from the gripper, So it's much closer to the object. And then we run it through some convolutional blocks and so forth. The action vector also gets fed in. And then what comes out is a Q value. The Q is the quality function. So if any of you have looked at deep reinforcement learning, you'll recognize this. And then we just train it using an off-the-shelf algorithm called DDQN, a double deep Q network. And we train it only on synthetic data that was generated by the simulated robot farm. And what we have is a pseudo-random policy generator that generates the training data. Sometimes it succeeds, sometimes it fails. And when it succeeds, then it gives it more information about how to succeed in the future. And because we have this robot farm, we can train these things in parallel and therefore get a massive speed up in training time. And for doing this work, we had to develop our own simulator that would model photorealism and physical realism at the same time. And then we have domain randomization on top of that. So these are just some of the results of that, where the robot is brought close to the object from dope, and then once it's close to the object, then it uses the closed loop feedback from that network to zoom in on the object and actually get a more stable grasp. And again, here's where we trained in simulation and then ran it in the real world. Now, if so there's still this question of how to overcome that mismatch between simulation and reality. And so, for example, in this case, we're trying to push this hockey puck on a table. If we don't know the frictional parameters of the table, then we're not going to be able to properly predict how it's going to move when we hit it. And so what we want to do is, through trial and error, learn to update the parameter distributions to better match what's observed in practice. And this is a technique known as Bayes-Sim, which came out of some colleagues in our lab a couple of years ago. And closely related work to that is this work on closing the sim to real loop. So we've talked about sim to real, but there's also real to sim. And if you put those together, you have this sim to real loop where you train in simulation, and it kind of goes back to your question, Joaquin. So you train in simulation, you apply it to the real world, and it doesn't work very well. And then what we do is we track, in this case, we have a peg on a string, and we track that peg using a depth camera and use the trajectory of that peg to update the parameters of the simulation. Then we go back, feed that to the simulation, update the training data, retrain the policy, refine tune the policy, run it again in the real world, and then it gets hopefully a little bit closer. And we use those tracks again to update the simulator. And we do this in iterative fashion. And usually after about 3 or 4 times, it converges. So the goal here is to swing the peg into the hole. There's a robot farm of 100 robots learning in parallel, just like we saw earlier. And this is using the PPO algorithm, if you're familiar with that, proximity policy optimization. So here are 2 problems. I'm sorry, here's the training data on the left, and then the results on the right. So you can see on the right-hand side, it's iteration 0 doesn't get very close. But then after tracking that peg and feeding that back to the simulator, the next time, which is iteration 1, we're getting closer to that hole, but still not able to get it in. Again, we track the peg using a depth camera, feed that data back into the simulator. Now the simulator has parameters that better match the real world. And now in this, which is basically the 3rd attempt, we're able to get the peg to go into the hole. And the same kind of technique can be used for other problems. So in this case, we're trying to open a drawer, and on the right-hand side, you can see iteration 0. We don't quite get close enough to open the drawer. Well, okay, so we opened it, but not maybe as well as we wanted. And so this is an easier problem, obviously, than swinging a peg in the hole. But you can see this time it's able to pull the drawer out farther than it did the first time. And the left side, of course, is the training scenario. Okay, so then I think this is the last project I want to talk about, and then I'll close. And that is the traditional approach for controlling a robot. So let's ignore perception for the moment, and let's just try to reach a point in space. Okay, so we have a goal up here in the top left corner. The robot's this thing in green. The robot has joint angles Q, and Q can through forward kinematics can be used to determine where the end effector is, x. So we know where the end effector is, we know where we want it to be. We take the difference between those, we feed that delta into inverse kinematics, and we use that to determine what the velocities of the joint angles should be in order to move the end effector closer to the goal. Okay, so this is a traditional approach. So what we're doing in this work, and we just posted this in archive, we just posted this in archive recently, but at the bottom, you'll see the archive link to the PPO algorithm, which is what we're using to train it. So we said, well, what if we replace that inverse kinematics with a neural network? And so now we have a neural network that just directly maps the goal to the joint velocities. And we train this using the PPO algorithm. Okay, so here's the paper that we posted to archive if you're interested. The nice thing about this approach is now if we can augment the network's inputs with information about nearby surfaces. So if there are nearby surfaces in the world, we can now not only reach the goal, but also avoid those surfaces, avoid those obstacles with almost no change at all to the algorithm. And that you just can't do with a traditional algorithm. With a traditional algorithm, it's a lot of work to incorporate obstacle avoidance into the reaching problem. And so how do we train this? On the left-hand side, you can see 4 different regions. So curriculum learning is crucial for this to work. So we train it on a smaller region, that purple region first. And once we train on the purple region, then we extend it out to a larger region. And then once it converges, then we extend it again and again. And we have 4 different regions, which are also shown on the right-hand side. You can see a plot of the iterations. First, we train it on this blue region until it gets down to that 1 centimeter threshold. The colors don't match exactly. So blue on the right matches the purple on the left. And then once it converges, then we increase the size of the training region, which immediately increases our error, but then it goes down over time. And then we just keep doing this. And then we have 4 different regions. And at the end of it all, we have now a policy that can reach any point in space in that larger region with sub-centimeter error. So here's just some examples of our robot in simulation trying to reach various goal points in the workspace. And we can reach pretty much any point in a very large subset of the whole workspace with sub-centimeter accuracy. The difference in radii between these 2 circles is 1 centimeter. And this is just showing you the training scenario. So we have, again, a farm of robots that can all work in parallel, learning to reach the goal position. And this is showing the curriculum learning. So we have a smaller region and then a larger region and so forth. And here we have the robot reaching a point while avoiding obstacles. And so those lines there are showing the distance from each point on the robot to the nearest obstacle. And those are being fed to the network to tell it which way to go. Here is a different robot. This is the Baxter robot, and we're trying to reach a point in space in simulation. And then after we train this in simulation, we apply it to the real robot, and without any fine tuning, it actually is able to apply it to the real world, which we find very encouraging. What's cool is that even though it works without fine tuning, you can take the exact same algorithm and architecture and just apply it to the real world data. And now you can fine tune it in the real world and get even better results than you would otherwise. So on the left-hand side, we have the same kind of training scenario. And on the right-hand side, if I can get it started, this is an application. Let me get my mouse back. This is an application of this technique where we apply, there's no perception here. We just provide waypoints, right? So we have waypoints in space, and we use that technique to map the goals of those waypoints to the actual joint motions of the robot to accomplish something in reality. So what we want to do is, of course, incorporate perception in this, and then we'll have, I think, something that's much more interesting. But this is the earth, you have to start somewhere. So this is the early phases of this research. So just to kind of pull this all together, we want photorealism and physical realism, I think, for these things to work. So that DOPE technique has some amount of photorealism, no physical realism, because it's just a computer vision problem. That SDR, structured domain randomization, has more photorealism, but still is working on a computer vision problem. The the simulated autonomous driving effort involves some physical realism, but because it's in 2D, it's not as complex as some of these other robotic manipulation tasks. And then we have, things like moving robots in space, training them in simulation to reach points in space, and then pour these bottles and so forth involves no perception, but involves much more physical realism in terms of how those joints move and so forth in space. This project involves some of both. And then finally, the project of swinging the peg is something where you have to have not quite as much photorealism, but much more physical realism in order to make sure that it's actually able to handle those complex dynamics. There's lots more that can be done here. We've just kind of scratched the surface in terms of future research. Large scale grasping of large databases, mobile manipulation we didn't touch on. Machine tending is where you have like a microwave or a coffee machine and you want to interact with it. There's a lot of problems there. In-hand manipulation, if you have an object, can you rotate it in place in your hand to reorient it? Something we haven't touched on. Tactile sensing, we didn't talk about. Object state changes. So if I have a cereal box and I open up the cereal box, it's going to be a topological change. It's going to be a different type of box now because the top is ripped open. Non-rigid objects is something that's introduced more challenges. Pouring liquids and so forth. Very fast movement is another challenge, and then generalizing to other kind of problems. So there's just lots and lots of open problems here for all of us to work on for many years to come. So in conclusion, I hope I've at least kind of whet your appetite or maybe even convince you that simulation is going to be a key for robotics in the future. That's for generating large amounts of labeled training data, as well as for quantitatively verifying the policies and algorithms. And I think what's key here is we're going to have photorealism and physical realism. Those are almost ready, but there's still more work to be done. And there are many open problems, right? And we've talked about these. Robotics is a wide open area. There's lots to be done. And hopefully, some of you are interested in helping us solve these problems. So thanks for your attention. Appreciate your time. And I'm happy to take questions.
Thank you. Thank you, Stan, for this amazing talk. We have a few questions. Anwar is asking, I have heard that NVIDIA is taking actions to prevent the use of GPUs in mining cryptos. Will this action be a limiter in the processing of big amounts of data, like in these examples?
Okay, the question is, will this be used to limit data in these examples?
So first, is that true that NVIDIA is taking actions to prevent the use of GPUs in mining cryptocurrencies?
So I actually have no idea. That sounds like a question for some business person at NVIDIA. Yeah, on the research side, we don't really get into those things. So what I can say is that NVIDIA is interested in their GPUs being, widely used for, as I mentioned earlier, for being the brains of these types of autonomous machines, right? And that spans everything from autonomous vehicles to robotic manipulation. And so, NVIDIA is very much interested in doing what it takes to make sure their GPUs can be trained and used for these kind of applications, for sure.
All right. Okay. Dagoberto is asking, do you train the model from zero to avoid obstacles while accomplishing the mission, or do you use some transfer learning approach?
Sorry, I couldn't hear you. What?
Do you train your obstacle avoidance models from zero, from scratch, or do you use transfer learning?
Oh, okay, yeah. So for the avoiding obstacles, we those are all trained from scratch. Yes. So those the videos I showed where we're reaching a point in space while avoiding obstacles, those were trained from scratch. But they're done so using, as I mentioned, a curriculum learning approach. So we start with an easy situation with no obstacles, and then we slowly add obstacles to make it slightly more challenging or increasingly more challenging for the network.
And a last question, Alejandro is asking, when training neural networks, are you keeping the norm of the weights below some threshold? This because your DOP work versus postnet are more stable, is more stable. Your DOP framework is more stable than postnet. So are you keeping the norm on the weights?
Are we keeping the norm of the weights?
Very technical question.
That's a very technical question. I'm gonna defer that to offline. Yeah, if you send me an email, I'll get you the answer.
All right. Okay.
I don't want to say it the wrong answer.
I lied to you. I'm gonna give you this question too.
Okay.
Are you exploring the use of transformers?
Okay. Oh, let me say though, our code is available online, so you can go to just type in deep object pose estimation. You'll get our code, and you can look at it all you want, and you'll see exactly what we're doing. Transformers, we're not doing. Let's see. I mean, there are people in NVIDIA using transformers for sure, but we and our little lab have not explored transformers. But I think it's worth. We've talked about it. It's very, very interesting work.
Right.
So, and I can see connections between transformers and some of the stuff that we want to do. So, yeah.
All right. Okay. Stan, thank you very much for your talk. It's amazing the work that you are doing. It is very inspiring. And I see a clear line that you are establishing, trying to make the robots accessible to a wide variety of applications. And I agree with you. I truly believe that the use of simulation is one way or one step that you have to take before taking these robots into the real world. Thank you very much for your talk. It was amazing.
Okay, great. Thanks everybody for your attention. Thanks again, Joaquin, for inviting me, and I hope that was helpful.
All right, thank you.
If you have any questions, reach out.
Y al resto de ustedes, pues muchísimas gracias por su atención. Y aquí los espera Luis Miguel en la siguiente semana en el seminario del CICATA Querétaro del Instituto Politécnico Nacional. Muchas gracias a todos.